This video is going to talk about three different reactions, all of which follow the same pattern and model. They are reactions that are classified as Electrophilic Aromatic Substitution reactions, or EAS reactions, and they deal with putting a substituent on an unsubstituted benzene ring. So I'd like you to recall that benzene has different reactivity than other carbon-carbon double bonds that are isolated or conjugated double bonds. And so we follow a general format for this. So we're going to take benzene. It's unsubstituted, but I chucked in a hydrogen just to show you guys kind of what we're doing here. We're going to put an electrophile bound to some good leaving group. So we're just going to say electrophile and good leaving group. And the product from our EAS reaction is going to be that electrophile substituted in where that hydrogen was, hence electrophilic aromatic substitution. The reaction has two main steps, so we're going to draw in actually a generic mechanism. Our double bond is going to attack our electrophile, and this is going to create a resonance stabilized carbocation, which you will see in a moment. So H, E is now part of the show. We keep these two double bonds. And so this is an allylic cation. We can draw resonance structures for this. Draw a little bit better bottom of the benzene ring there. We can have double bonds here and here. Or we can move the cation there. What's going to happen then is this leaving group that now has a negative charge is going to come in. I'm just going to put one lone pair on it. Legibly. There we go. It's going to deprotonate. This bond will pop back in to restore aromaticity. And we've substituted our electrophile onto the benzene ring. The first type of EAS reaction we're going to talk about is halogenation. This works with bromine and chlorine, so Br2 FeBr3 or Cl2 FeCl3. Whenever we have these reactions, it is very important that we show the electrophile so we know what exactly is adding onto our benzene ring. For halogenation reactions, you'll always have some molecular halogen. So Br2 or Cl2, I'll draw nicer lone pairs for you. Much better. A lone pair from that diatomic halogen is going to come over, attack the iron, and we will have... So remember, these two are still bonded together, and now they're attached to FeBr3. This Br is positive. Remember, it has two lone pairs on it. Probably should have drawn those in before the positive charge, but you get the idea. This one has a partial positive charge. Iron, of course, in this case, has a negative charge. And the way this turns out for halogenation reactions, this end halogen is the electrophilic atom. So I'll write that in, electrophilic atom. Now we can come down here to our benzene ring. And draw in the same thing that we drew in our generic example. So double bond attacks electrophilic atom, bond to the rest of the electrophile breaks in this case. And then we're going to draw, wow, there we go. So we have our cation up here, our hydrogen along with our bromine, and we're going to keep these two double bonds. Then we must show our resonance structures, which you guys will get better at these as you do them more often, but also drawing hexagons, which sometimes works out great and other times really doesn't work out great. It happens. Okay? And then what happens again is that negative ion that we created, so, sorry, Br, is going to come in, deprotonate. We're going to restore that good benzene look, our aromatic ring, nice and stable. And we're going to have our bromine substituted in on that benzene ring. In terms of the overall reaction, we can come down here just so we always have a conceptual idea of what we covered on this page. So, undo. Draw in our benzene ring, Br. So if it's just a predict the products question, that's what you'd write. I think it's worth pointing out really quick that, and this is just, it's like a this does not happen. So if we have a benzene ring, right? And let's say, we have just the same E and X. Okay? This does not it does not add across the carbon-carbon double bond. No, 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 no. Okay? So, yeah, you are substituting in for a hydrogen. You are not adding across a carbon-carbon double bond like you've done in Orgo 1. So this is not the same type of reaction. Sorry, I just thought that was worth pointing out very quickly. The next type of EAS we're going to talk about is called nitration. We're going to add a nitro group, so an NO2 group onto a benzene ring. We need to show the formation of the electrophile for this as well. So sulfuric acid and nitric acid are used for this. Of course, sulfuric acid, great source of a proton, 2 acidic protons on there. So we are going to take this oxygen right here. We're going to protonate our nitro group. We are going to end up with this. It's a minus sign. And then this. And if you'll notice, this right here is water, and it's a phenomenal leaving group. So water is going to leave. One of the lone pairs on this oxide is going to come in. Make that double bond with the nitrogen, and this is our electrophilic atom. So now we can come over here and draw our mechanism. So we draw, again, our electrophile. I'm going to draw it like this. I know it's linear. Well, no, I'm not. I'm going to draw it linear. I don't want to do it incorrectly. So double bond comes over here. Much better. Makes a bond with our nitrogen. When that happens, one of the bonds to either of these two oxygens has to break. I've chosen the outside oxygen just because it makes my arrows look a little bit more continuous. You can do this however you want. There is no better way to do it. They are chemically equivalent in a sense, so do not worry. So now we have our benzene ring. Well, it's not a benzene ring anymore. 2 double bonds. Remember, we have to draw in that hydrogen. Remember, one of the oxygens has a double bond, one of the oxygens has a single bond and a negative charge. Nitrogen has a plus on it. So now we go ahead and we draw in our resonance structures, moving that positive charge around the benzene ring. And again, once you do these more and more often, you will get more and more used to drawing them. And we're going to go, sorry, my bad, here and here, plus H, N, O, O. So now we can draw in the conjugate base of sulfuric acid, and I'll do that in a different color for you, just so you can see that it is that's coming in, deprotonating, restoring aromaticity to our ring. So now it is a benzene ring again, where we've added this nitro group, but for all intents and purposes, you can just write it out as this, and we'll know exactly what you mean. So again, we come in with our overall reaction, just so you have a summary of what's on the page. Down. There we go. Not even. So you guys notice that I spend a lot of time in my videos, like erasing and rewriting. This is because if you're watching this video to review or you're watching this video to learn it, I want it to look nice so you understand exactly what I meant to write down. So there's no question as to what I'm telling you. Let me actually, I just want to redraw this right here, just so it's 100% clear that I'm not connecting these two sulfuric acid atoms. So anyway, we're back over here, nitration product, benzene ring with an NO2. If you're asked that on a predicting products question, that is what you write. The last EAS reaction I'd like to talk about today is called sulfonation, and we use fuming sulfuric acid to add a sulfonate group to this benzene ring. Fuming sulfuric acid is a mixture of sulfur trioxide and sulfuric acid. So, formation of our electrophile, we're going to start this in a very similar way that we made our nitro electrophile. We are going to take this oxide right here. We're going to protonate our sulfur trioxide with sulfuric acid. This is an equilibrium step. And we have our electrophilic atom right here. And then we also, just for the sake of writing it down, make the conjugate base of sulfuric acid again. And that will come into play again as well. So chances are if you have sulfuric acid, the conjugate base will be active in the mechanism somewhere. And I think that holds true to Orgo 1 as well. So let's draw our mechanism. I'm going to draw the OH group in as OH. I know I drew out the oxygen-hydrogen bond right here. I'm going to write it as this just to keep this a little bit neater for you to read. Double bond O, plus. We'll actually write that on the other side because now we will have double bond from the benzene ring, attack, pop off one of the double bonds on one of the oxygens. Does not matter which one, they are chemically equivalent. You may choose either one. So now we draw in, and I will actually draw this out. OH, O, O. And we have, here and here, cation. There we are. So we can draw resonance structures for this, which we will do every single time we do an EAS mechanism. Every single time. I know it gets old, but it's very important to show you know what you're working with. And I'll put the lone pairs on this oxygen just for all intents and purposes, showing all of my work in a math class kind of term. Last one. So now we know we have all three resonance structures done. We can now come in and draw the conjugate base of sulfuric acid again. coming in, deprotonating. We're restoring the aromaticity on our benzene ring. So we're putting that double bond back where we originally had it. And we end up with our SO3H group substituted onto our benzene ring. We'll just chuck little pluses in there. I try to show formal charge as much as I possibly can. And you can write it like this, or for all intents and purposes, you may just write SO3H. That is perfectly reasonable. Coming down to our overall reaction, we will just draw our benzene ring with SO3H. So predicting products question, if they ask you that, that is what you write. And that'll do it for sulfonation and for this electrophilic aromatic substitution video. I hope this was a good intro to you. If this is your first time seeing these reactions, or if you're doing this in a class, I hope this served as a good review, both for electrophile formation, drawing products, and drawing the mechanism for EAS reactions. Remembering those resonance structures is a really, really big part of drawing these mechanisms, so we understand how that positive charge can be delocalized around the six-membered ring. And I think that will do it for this video, and we'll see you next time in Friedel-Crafts.